you have seen last time we had I left you an exercise that has been also published on learning with numbers as a result, and I don't know if you have done it. So I would like to just repeat this exercise with solution, but I hope you have tried by yourself taking the text from e-learning. So the exercise was to consider a vehicle with 5 rocket engines with an amount of propellant equal to 70% of initial rocket mass. It's true. Thank you for. You can also talk with me, not only with your colleagues. Don't be shy. Here is the whiteboard. So we have. We don't make a break today. Each rocket provides the same thrust and specific impulse, and you assume that both they are not changing in time, but specific impulse and thrust. You assume that specific impulse is 260 seconds, and the first question is, what is the maximum time it can last to consume all the propellant, provided that thrust allows to lift the rocket? So we have 5 rocket engines, and we have that the amount of propellant, MP, is 0.770% of the initial rocket mass. So the first thing to do is to evaluate the maximum time needed to consume the propellant. So we have that this time is simply, of course, the propellant mass divided the propellant mass flow rate, and the propellant mass flow rate is related to the thrust level and specific impulse, and the thrust level is related to the mass, the initial mass of the vehicle. So we have that F with 5 engines is, let's say, alpha m0 g0, where alpha is the acceleration we have a liftoff. So it should be 1 in our case. And this is also 5 times the mass flow rate of the single engine by the specific impulse. Or we can also write this in this way, dot m5 UQ. So with this, we can evaluate our time as maximum time, which is equal to the ratio between the propellant mass and the propellant mass flow rate. And this would be this 5 here, the whole amount of mass flow rate we are exhausting. And so here we obtain this dot m5 is F over UEQ. And then this is also M0 G0. I wrote this with a specific impulse in seconds so that I can simplify here. And you see that we have just if alpha is equal to 1, we have just ISP J. and the result is 182 seconds. Now, if after 10 seconds, one of the 5 engines fails, how long it will take to consume all the propellant? To do that, we have to consider now that the whole time, or better, the propellant mass, will be the sum of 2 contributions. The first part, which is consumed before engine failure, and then a second part with 4 engines rather than 5. And so with this, we can easily see that we have that the time if I divide by dot m5 here, I have that this Tmax is equal to Ta plus 4 Tb. And so also the second point is practically solved, because we have just to take this expression and evaluate now the time, which is Ta plus Tb, the whole time. So we have T max is equal to Ta plus 4 Tb. We know that Ta is equal to 10, because we said after 10 seconds we have this failure. We know that we have just computed this value, which is 182 seconds. And so we can evaluate Tb, and the result is, I have not the result, so it should be this, so that Ta plus Tb is the new time, which is 225 seconds. The third step was, is at this time of 10 seconds, just after failure, the vehicle able to lift its weight? And as we have no other questions, we know that the answer is no, but we can check. So we have that at this time equal to Ta equal 10 seconds. We have that thrust is, of course, we have 4 engines, so it's 4 times the single engine, and so 4/5 of the thrust with 5 engines. So the weight at this time of 10 seconds will be, let's say, ma this time A by G0 will be the initial mass minus the consumed mass dot m5 Ta by G0. We recall that, of course, we have that F is m0 G0 F5. And so we can see that now F4 over MA is 0. Will be equal to 4 over 5 F5 system 0 G0 over MAG0, which is M0 G0 minus dot M5 TA G0. Dot M5 again is F5 over UQ, so it's again M0 G0 divided by UQ, and so in M0 over ISP. I can substitute here and simplify here G0 and then also M0. So this becomes one minus T A over ISP. And the result is 0.8 and over 1 minus 10 over 260. And so we have 0.832, which is less than 1. So the answer is no. And so we can move to the fourth question that says that if answer is no, what is the minimum time needed to allow safe failure of one engine? So in practice, we have to take this expression and evaluate this TA to have this value is equal to this value is equal to 1. So to have, if this is trust to weight ratio, we need that F over W should be greater than 1. And we can find that this minimum time is again 4 over 5, 1 minus T over 260 should be equal to 1. And it follows that T is 52 seconds. So this, in this computation, we say that we can safely lift our rocket even if one engine fails, but this must occur after 52 seconds over the whole duration of the operation. The final question was, what would be the trust to weight ratio needed to guarantee that one of the engines can fail after 10 seconds? Of course, this is just an exercise. We don't want to have a minimum time of the engines, of operation of the engines, but we can estimate this. So what should be the trust to weight ratio at liftoff to guarantee that even if we have failure after 10 seconds, we can continue to lift our rocket. So if you take this expression, you go back here, in general, if when I make the equivalence between the thrust and the weight of the engine, this one, this is because I'm considering that M0 G0 is equal to, yes, this one. In this case, I'm assuming that we have just exactly the thrust equal to the weight at liftoff instant. So if we put an acceleration here, multiplying quantity, we have now that this is something strange here. This should be M8. This zero. We see here this should be 4/5 of. Well, I think it's better we write it again. We have F over weight, so we have 4/5 F5 divided by M0 G0 minus dot MA G0 by TA, right? Dot M5. This is what I wrote before. Dot M5. G0 TA. This should be correct. And this must be equal to 1. And our unknown now is F5 in a sense. So F5 will be 0.8 alpha M0 G0. Well, alpha is this acceleration that we took 1 in the first case. Whereas we have here M0 G0 minus dot M5 is again M5 over the exhaust velocity or the resistance part, so it will be alpha M0 G0 over, this is F5 divided by U EQ, and then we have G0 TA. So we can simplify and divide everything by alpha M0 G0. And minus alpha, 1 over alpha minus TA over ISP. Ok. Che manca? No. Portata per tempo e massa. And so the result here is that alpha assume this value. And in this case, this corresponds to a shorter time, of course, of operation. That will be 152.6 seconds if there is no failure, and 188.2 seconds if there is failure. Let's pass to another exercise now. Okay, it's clear this exercise? Yes, we have, because we have a given amount of propellant and we know that we have thrust and specific impulse which are constant. That means that also the mass flow rate is constant. So just if we have a given mass flow rate, we will consume all the propellant in the time that comes from the division between the available propellant mass and the rate at which we are consuming propellant. This is just simply dot MP is just propellant mass over time, or delta T, which is constant, and so we just simply use this relation. It's clear for everybody? Okay. Okay, let's move to the next exercise. And this time we make something, let's say something strange. We assume that we are flying with a rocket at a constant speed, which is not typical for the rocket, for 100 kilometers. And we also with constant thrust. So we assume that our thrust is 1000 Newton. We assume that our constant velocity is 1000 meters per second, and we are flying for a length, for a distance of 100 kilometers. So assume we are flying with this rocket, for instance, for this length from this point A here to a point B at a given altitude with this length, 100 kilometers. This is the exercise. What we know, we would like to compare two cases. One, where we have an exhaust velocity, or equivalent exhaust velocity of 1000 meters per second, and another one where we have twice this specific impulse. So what we like to know, the propulsive efficiency in both cases, and the total propellant mass used to go from point A to point B. How much mass we are going to consume. Then, if you assume that the chemical energy released by 1 kilogram of propellant is 10 megajoules, so if this Q is equal to 10 megajoules per kilogram, we would like also to evaluate the overall efficiency, the residual power of the jet, and the internal efficiency. Think a minute about this. Yes, the overall efficiency and internal efficiency and residual power of the jet. Are you trying also at home? So propulsion efficiency. You complete propulsion efficiency. In the first case, is trivial. Residual power of the jet in the first case is trivial. Who is so brave to give this answer? What? In the first case, propulsive efficiency is 1. The exhaust speed is equal to the flight speed. And what will be the residual power of the jet in this case? 0. So let's look to the second case, where we have a ratio between the flight speed and the specific impulse, which is nu equal to P over UE, and in this case is 0.5. We recall that the relation between the propulsive efficiency and this ratio of velocities and the result is 0.8. Of course, this is the expression for the rocket. So what is best? To fly with a rocket having an exhaust speed, or let's say, if it is adapted exhaust speed, the specific impulse is the same. So let's assume that this is our exhaust speed or specific impulse, we'll call it in both ways. So what is better of these two cases? Propulsive efficiency says that should be better the first case, because we have no residual power of the jet. But let's see actually what is the meaning of this velocity. So if we have a given propellant characterized by this power, this available energy, we can evaluate the overall efficiency, and we see that actually is better the second case. And in fact, you know this from the beginning, because you know from here, as this is a specific impulse, that the higher value means that you have the same thrust with half amount of propellant mass. So at the end, you will spend you are flying at the same speed for a given length, so for a given time. In that time, you will spend half the mass of propellant, and this is what we are trying to get to save propellant. So the residual power of the jet is 1/2 dot np UE minus V squared, and it will be in the first case 0, in the second case 0.25 megawatts. And we can now evaluate, say 1 and 2, the available power is the delta MP by QF. I wrote before, right? It was QF or Q, sorry. This Q is how many joule per kilogram we have available. If we are considering, we are using given kilogram per second, we have to multiply by this quantity, and we have the available power or the available energy per second that you are providing by consuming this propellant. So if I make the multiplication here 10 by the flow rate, and the flow rate, of course, is something known because that MP is F over UE in both cases. So that MP will be 1000 over 1000 or over 2000. So in the first case will be 1 kilogram per second, and the second case will be 0.5 kilogram per second. So as a consequence, 1 multiplied by 10 means 10 megawatt in this case, in the first case, and 5 in the second case. Useful power is 1 and 1 megawatt. This is the same because the same thrust and flight speed. The residual power of the jet, we say that this is 0 here and the 0.5 here. And the sum of PU plus PR, which is the energy I provide to the jet, will be here 1 and here 1.25. The propellant mass, we say that is 100 kilograms and 50 kilograms in the two cases. With these powers, we can evaluate the internal and overall power. So in particular, we have that, the overall efficiency is PU over P available, and it will be 0.1 in one case and 0.2 in the second case. So of the available power that we have here, in the first case I just used 10%, in the second case 20%, and this because we have a higher internal efficiency that transforms. Of course, this can be computed as the ratio between these two efficiencies, and we have here in the first case 10%, and in the second case 25%. Okay. So we see that propulsion efficiency is something important if you are using, let's say, we are separating the internal and, let's say, propulsion efficiency. That means we are using a propellant flow rate from one side and an external medium on the other side. In case of rocket, what is important is how to convert the internal energy, the available energy, in jet power. You can also play the numbers and see that you can obtain the 100% internal efficiency at the best. So 100% internal efficiency means that you are considering an exhaust equivalent exhaust velocity of, so to get this equal to 1, we need a higher exhaust speed, so we still have a residual power of the jet, in this case is greater, we have 1.3 megawatt as the residual power of the jet. And we have propulsive efficiency, which is 43.6%. So we still have inefficiencies, but it's better. Also, the exploitment of what we have on board. Grazie. Dovrei fare più errori. So let's consider a further exercise now. What we do here, we consider our rocket flying just vertically, and we have the gravity force acting on it. So we like to consider in the first part of the exercise what will be the altitude reached by this rocket when it has consumed the whole amount of propellant. Okay. We know that actually if we are going up in the atmosphere, the ambient pressure is changing, so we should take into account that also thrust is changing. If we consider constant mass flow rate, we have the pressure term that tell us that thrust is increasing as we go up because pressure is decreasing. So we have a linear increase of thrust. Well, let's consider the data. We have an initial mass of 150 kilograms, a sea level thrust of 2200 newtons, propellant mass of 100 kilograms. We know that this is adapted at sea level. We have also that the exospeed, this case, is actually the exospeed at sea level. So where we have this adapted, so the effective, not the effective, the actual velocity at the exit of the engine is 2200 meters per second. And of course, we know that here EA is equal to 100 kilopascal. Then, on one side, we also note that we have RE, the radius actually corresponding of the exit of the jet, is 3 centimeters. And we can assume that pressure is the sea level pressure we have an exponential law to decrease pressure within the atmosphere for the sake of simplicity. Okay. So, first of all, let's calculate the final altitude reached when we consume what amount of propellant if we assume constant thrust of specific impulse. Then we see what happens, what will be the final altitude in this case during this operation, and we can check what would be the thrust and specific impulse at that altitude. As a consequence, we can estimate what happens with changing atmosphere by considering an average between the initial and final specific impulse. It's clear? We are going up vertically. Up this point. And we have of course the gravity force mg, and we are considering, so this is C, 0 at sea level, and we'll have a given velocity that we reach at this point. In this direction, but this is, at this point, we end propellant. So we stop our engine. So the question is, what is this? See, in a first approximation where we consider constant thrust exactly as in the at sea level, and the second step will be to get a new estimation of the constant thrust level, exploiting the information that you have got with the first tentative value for the thrust at the final elevation. Per ora quanto tiene il propellente? We are looking for this final altitude when we complete our thrust period, thrust operation, because we are looking for the information related to the thrust level. And so we have to consider the pressure that we have all along the period with thrust active, with the engine, with operating engine. Of course, we are neglecting drag from the atmosphere. Question from home. Are you trying to make the exercise? So of course we have an acceleration changing in time. So we have to make an integration to get the velocity and then the position in this one-dimensional problem along the 8. We start with zero velocity. Okay, and then we have also the next step will be the position. Okay. You agree with this here? And so let's move this. So at the end, we can get an expression of velocity as a function of time during the thrusted phase. That will be minus gt plus f over dot m that multiplies logarithm, and then we can evaluate this at initial and final time. And of course, difference logarithm can be also seen as the ratio of their arguments, and we can invert it, and so write this with plus, and make between t and 0, and in 0 we have m0, and in t we have m0 minus dot mt. This is the function of time. Then, when we have now to integrate this, and this will be minus 1/2 gt squared and now we have these two terms. I can write this also minus gt plus f of m. I can write it also in this way, and then so when I make the integration, this is a constant, so just to multiply by t. And so, of course, I made the integration between 0 and t of this first term. It's, of course, minus 1/2 gt squared. And then this is a constant by t. It's the second term. Finally, we have this last term, which is slightly more complicated because we have the integration of a logarithm. So the next step will be just to solve this integral, and so that we obtain the solution. And by integration, we can use integration by parts and see that this is equivalent to the following. We see that S over 3, sorry, will be minus 1/2 gt squared plus. So I assume that you can do that integration. Okay, if I give you this exercise, you can solve the integral. And this, and then 0t plus 1 over dot m, and then we have the integral between 0 and t of d no, it's already differential form. And all this should be by F over dot F. So we have this expression, and you can then go ahead and evaluate this integral. Okay. What you find, I give you the solution here, is so if this is the final reactive at the end of burning of the propellant, can you estimate the new specific impulse now? So taking the average, considering what will be, let's say, specific impulse of thrust, of course, we can evaluate both. And I have, yeah, so it's okay, it's the same, because we have just 1 kilogram per second, so it's quite easy to consider the equivalent exhaust velocity. And thrust is a little different, it just has the same numerical value. So what you should do now is to evaluate this pressure term that appears because of the decreased ambient pressure. This should be something that you can do also easily, and you should know very well. So of course, what we do now is just to solve the exercise with just paper and pen and calculator. But you can, of course, make also a correct integration and solve the exercise, say, in detail by integrating the governing differential equation by considering the fact that the thrust is changing with the altitude. So at the end, you can check to put that second order equation in MATLAB, and you have the solution. But to implement the right governing equation in MATLAB, you should express the thrust as function of the altitude correctly. Yes, yes. This is with the first step that we did is to consider constant thrust the same as at sea level, and we assume this is obtained by G0 is equal to G 9.8 meters second squared. And with this data, just replacing the of course, this will be written at time t and at time 0 at quantity. I just going to the right to don't waste too much time writing. But this is something that can be obtained analytically. Of course, you don't have the solution, analytical solution, if you remove the assumption of considering constant thrust. So to keep this assumption, we can consider some average value, at least, to see, let's say, the order of magnitude of change. If we have that altitude changes, if I take the new thrust and I obtain, as a result, 50.120, we can say that probably considering an average value is correct. Is constant or average doesn't change much. Of course, if we have something like 5 kilometers more, that means 10% change. Of course, probably taking this average as mean average, as arithmetical mean, is not correct. It's just to have an idea. But when you have to show that you are aware that there is a change of specific impulse due to altitude, we can consider an average. For instance, if we are making, if in an exam there is an exercise where we have a first stage contribution starting from sea level, we have, and so it operates up to more or less vacuum, we will consider an average specific impulse that will not be the integration along the trajectory, but just, let's say, the arithmetic mean, to show that we have an idea of what we should do in a correct solution of the problem. If you don't care about that, it seems that you are not aware. So do we have pressure, at least? Mm-hmm. and then we can easily obtain from here. Okay, so we can take an average value if we consider an average value. We have this, that also means if you average is the same because we have 1 kilogram per second. And the result of applying this expression, now I write it, so minus 1/2 ct squared plus if we put now this second value of f, this expression, instead of having, what we know is that as we have mp is equal to 100 seconds, and we know f and dot m, we have calculated this, which is 1 kilogram per second. So we can put 100 here, and we have our value of c. Okay, we have dot m, we change f in the two cases, and the difference is that in the first case, we say that we have 50.119 kilometers, and in the second case, we obtain 56.478 kilometers. And this is to say that, well, there is a significant change because of the change of thrust with altitude. Consider that if you make the correct integration, the result would be slightly less of this. So let's say integration yield so I leave you this as an exercise to get the integration numerically by it's just the integration of second order differential equation with known initial conditions. And I also would like to review the following. So I think, I don't know if you have seen, the second part is inspired of what you have seen on the media yesterday. It was about the attempt of SpaceX of landing SN10 rocket. So in that case, we have a more complex maneuver for sure, but as let's say, the basic is that we go up and then we go down. And we accelerate, reach an altitude, let's say we reach at, to simplify the problem, we reach a maximum altitude, then we start going down, and at a point we start our engine to slow down and to stop. So what we can do is just considering it vertically. We take this exercise and we stop here at 50 kilometers or 55, 56 kilometers. Then we leave the rocket go up to 0 velocity, and then it will fall down. We have here, we have considered 150 kilograms of initial mass, and it was 100 kilograms of propellant, right? Let's now consider that among these 50 kilograms left, we can have some propellant to be used with the same engine during descent. Of course, let's make the computation with constant thrust, else it becomes more complicated. But you can do by integrating your differential equation. You can also do it correctly, this procedure. And we have to see if we are able to slow down up to 0 velocity when we reach theta equal to 0. Okay? Okay. Dipende, ne hanno provate tante. So they try different attempts. Because of course, there is two things that you have to take into account. One is the mass is less when you are going down. And so the thrust to equate, to be equivalent to the weight has to be less. But of course, you can accelerate more or less, depends on when you start the engine. Sì. Ah, sì, ma sì, ok, lo fanno. Lì è chiaro, se tu stai andando su e spingi di meno e prevale la forza di gravità, vuol dire che non acceleri più, che rallenti. Quindi loro, in effetti, bisognava arrivare a una certa altezza, poi fare la manovra di discesa e di riverticalizzazione, quindi a un certo punto dovevano spegnere, ma lì soprattutto spegnere e accendere è per provare il motore, quindi è per vedere se sono in grado di riaccenderlo più volte, tra l'altro in breve tempo. So we can try to do this exercise, and the interesting thing is to find, of course, it's something that in this case you have the final solution, you're not the initial one. So probably you have to find some trial and error approach. And what you'll see is that you can identify the moment. In this case, you are considering always the same thrust, always the same engine. So there will be the right moment you have to light your engine. Because if you start the engine too late, it means that you will crash. If you start too early, you go back. And so you can find analytically, you can find nice exercise, the right position. Okay. So I'll try to to write this text on the website so that you can have it in front and try. Please let me know if you try what will be the results. I will be happy to see that you are trying to make some exercise.
Considerando quello che utilizziamo per la caduta, si può trattare con il quadrante.
Yeah, okay. A correct question has been posed about propellant mass. So we have that what is the payload for the ascending phase, this 50 kilograms, can be in part propellant. And we have to evaluate, depending on this trajectory, there will be an amount of propellant used that has to be used, and in principle you have to take into account before defining your mission. So you will see that in fact we can manage it. So you can have something between 20 and 30 kilograms of propellant is what is needed for the descent, for the safe descent. So you can compare that you needed 100 kilograms to go up, and then because of the less mass we have, you have to just use 25, 30 kilograms of propellant. So there will be left something like 20 kilograms for everything else, tanks and so on, payload, control, engine. That of course is not realistic, but this is an exercise.